Welcome back. So in the last video we showed how we could reduce the information needed to represent an image by doing one of two things. So you can either reduce the amount of information needed for each pixel of the original image, so this is where we reduce the number of bits required to generate a single pixel, or we could start removing values from the discrete Fourier transform of the image, and then inverse discrete Fourier transforming the discrete Fourier transform to reconstruct the original image, but with those components missing. And what we found was that for a digital photograph, such as these ducks here, we had better results when removing values from the DFT. Whereas for images like text images, we had better results from reducing the bit depth per pixel. And this was explained as digital photographs are complex images and so have a lot of information distributed across all of the pixels, and so removing items from its discrete Fourier transform meant that that change was distributed across many pixels, which are all quite complicated, so it was much less noticeable than changing individual pixels themselves. Now what we're going to do in this video is show how by breaking up this image into discrete blocks, so for both the text-based image and for the digital photograph, and then performing the discrete Fourier transform on the individual blocks, we maintain our ability to remove Fourier transform components from our digital photograph, but also improve our ability to remove components from the DFT of the original text-based image by localizing any artifacts associated with it. Let's go ahead and get started. So I have here an empty file, and we can go ahead and copy some of the code we used over from our last video. So I'm just going to copy over some certain things. Okay. And now we're going to add in a variable. I'm going to put block size. And the aim here is that we're going to try and chop this image into much smaller blocks of size 8 by 8 in this example, and then apply the discrete Fourier transform to each one of those blocks. So the first thing we want to do is to actually be able to plot this. So the first image we're going to want to plot is the original image on the left, and then also a description of the original image in the Fourier domain, but in terms of blocks. So how are we going to do that? So we've defined our block size. We're going to change this part of the code in order to ensure that the image is exactly divisible by the block size. So for example, this image is 64 by 128 pixels. Both of those are divisible by 8, that's fine. If, however, we had an image that was say 121 pixels, then we know that the closest integer number of block size that fits in there would be 120, so it crops the image to 120. It does that for both axes. So that's how we do that. We're also going to need a plot. So here I've defined a plot. It's going to be 12 inches by 12 inches. It's going to be a single row with 2 columns. And then we've taken the aspect ratio of the original image in order to scale the height to the aspect ratio. So if the image is very wide, then the plot will resize accordingly. So let's go ahead and plot this. So this is code copied over from our previous example. When we run this, we see on the left we have our original image. Good. Next thing to do is to generate the discrete Fourier transform on the right hand side, but in blocks. So how are we going to do that? So first of all, I'll put a little hash box in, explain what we're doing. So calculate the DFT for the image in blocks, e.g. 1024 blocks with an 8 by 8 discrete Fourier transform describes an image that is 256 pixels by 256 pixels. And also calculate the resulting image array im3. What does that mean? So first of all, we're going to need a blank image array. So im3 will be our representation of the block-based discrete Fourier transform. We're also going to create another array. So this will be of shape ny over block size, nx over block size, block size, block size. So it's going to be a 4-dimensional array in which the first 2 indices are whereabouts in the image that block is. So indexed in numbers of blocks. So for example, the image is 128 pixels wide. We know that's 16 blocks wide. So this would be 0 to 16. Sorry, this would be 0 to 16. And it's 64 pixels high. So we know it's 8 blocks high. So this would be 0 to 8. Or 8 not inclusive, 16 not inclusive. And then block size to represent the actual 8 by 8 DFT at that block. We then need to go ahead and actually implement the DFT in those blocks. So what this does here, we use iter tools, which we imported at the top, which gives us a nice iterator. So what we can say is loop over the entire image rows and the entire image columns, but step by block size. So start at 0, then go to 8, and then 16, etc. And then for each one of those, find the corresponding block number in the original image. So for example, I will iterate through 0, 1, 2, 3, as ny iterates through 0, 8, 16, 24, etc. And then what we do is we set that element of the array to the DFT for the same block in the original image. Okay, perhaps it's better if I go ahead and run this, because what we can see now, not going to let me view this, but you see the block FFT has a dimension of 8, 16, 8, 8. So it has 8 blocks high, 16 blocks wide, and then each one of those elements has an 8 by 8 DFT associated with it. We can then go ahead and build up an image representation of this DFT, because now the DFT is a 4-dimensional array. What we want to do is put those DFT elements back into an array so we can plot it. That's what this function does here. We're basically saying create a new blank array called imFFT_block. So this is our blocks-based FFT image. It does the same array that we saw just above, but now it iterates over this newly created array and inserts where the block size is, where that specific block is. It inserts the element from the block FFT. What do I mean by this? So if I go ahead and run this and then look at the imFFT block, you see it's an image 64 by 128. So it's the same size as the original image. Let's go ahead and plot this. So we can use the same syntax as we always do for plotting. We can do axis on the right, because remember at the top and from the previous video, we created an image with an axis on the left and an axis on the right. We can then go ahead and say, take the axis on the right, give me an image. It will be the absolute magnitude of the block-based Fourier transform as we've just calculated, and it will be the log of that, so you can see a larger range of the numbers. And again, we make sure the extents go from 0 to nx and ny to 0, so that the pixel itself goes from 0 to 1, for example. Now if I go ahead and run that, we should see we get a block-based Fourier transform. So what is this? So for each 8 by 8 block, we're basically calculating the DFT, but we're then plotting that DFT in with the original blocks. So for each 8 by 8 block, for example here, if you can try and make it out, you'll see that we have an individual discrete Fourier transform. So there's a large value in the top left corner, so that's a DC offset, and that's typically the largest value, especially considering that the same 8 by 8 block on the original image is taken up by an almost completely white pixel. Let's go ahead and see if we can visualize this better. Say on this image, why don't we draw some red lines every block? So it's going to loop over all the pixels corresponding to the block edges in the Y, loop over all the corresponding block edges on the X. Then it's going to plot a red line vertically or horizontally as required. We're also including a Z order equals 2, which means that this will be drawn on top of the original image. And in fact, let's go ahead and do that for both images. X1 left is the image on the left, X1 R is the image on the right. Go ahead and plot that. You see now, so our original image is divided up into these 8 by 8 blocks, and the discrete Fourier transform is calculated for each block. Let's go ahead and find a block that might be interesting. So we can see this block here has a nice variation across it, and we can see that a DFT in that region produces a unique DFT corresponding to that block. Likewise, you can do this for all of the blocks. And what's interesting here is that you see now the DFT does not have any components that are non-zero, but the parts of the image which are non-zero. So this is a really nice way of breaking down the image to localize the DFT. And each one of these DFTs contains 64 elements, which is quite a nice number of elements. And so removing elements from this should still be quite practical. Let's go ahead and see what happens when we change our block size, say 16 blocks. You can see that the image is now subdivided into much larger blocks. And so more of the image is taken to describe the discrete Fourier transform for each of those blocks. But that does not mean necessarily much more information is required to describe the image, because a lot of these components could be very close to 0 or not needed. We can also go and say, oh, let's make a block size of say 1. This is an interesting case. because it basically means that each pixel now has it's a single pixel discrete Fourier transform, so it's just a single number used to represent the brightness in the frequency domain of the original image. So removing pixels from here would be no different to removing pixels from here. Likewise, if this image was square, we could make the discrete Fourier transform the exact size of the image, and then we would have the same discrete Fourier transform that we had previously. But here, see, for large blocks. Let's stick with 8 by 8. 8 is quite a common block size for things like this, with 64 different values within each block. What we're going to do now is we're just going to print out some information. Is say, take the sum of all the elements of the block-based FFT, which are equal to 0, and divide by the total number of elements. This will tell us how many elements of the block-based FFT are 0. If we see here, it's printed out 37.6% of the elements are 0. Change the block size again to say 4. We can see 21% of the elements are non-zero. Block size of 2. 13% of elements are non-zero. So the amount of non-zero elements decreases, or seems to decrease, particularly in this example with our block size. That won't be true for a digital photograph. But that's useful information to have. I'm going to go ahead and add some titles to our plot. So here we've used a NumPy fast string, so it's going to type in log underscore, and then we do double curly brackets because we've surrounded everything with $signs, which means we are formatting with LaTeX. So double curly bracket to have 10, so the value 10 will appear. We're then going to write the absolute value of the DFT with an underscore, and then we're going to dynamically insert our block size. Remember, we need to use double curly brackets so that LaTeX knows that this is a LaTeX escape character, and then another single curly bracket for the F string. Go ahead and plot that. We see at the top we get a nice little description of what this image on the right is, and then same for the left. If you want, you could go ahead and save that. So type in a command like this, fig1.savefig. Remember, fig1 is the figure that we created to hold these two axes. And just give it a name such as DFT underscore block size by block size PNG. And again, using a fast string, so the value between these curly braces is evaluated, which in this case will be 8. Okay, this is very good. Now, what we need to do is we're going to have a plot where on the left-hand side, we have a blank image, and on the right-hand side, we have all of the basis functions required to describe this block-based transform. So each 8 by 8 block. So we're going to have all 64 basis functions on the right. Then what we're going to do is show how adding each one of those basis functions to each block constructs the original image, or reconstructs the original image. We're going to do a little hash box, hopefully describing well what we mean to do. We need to create an array for our basis function. So again, this is going to be an array, but now it's of shape block size, block size, block size, block size. So it's a 4-dimensional array. It's an 8 by 8 array because remember, we need 64 basis functions, and each basis function itself is an 8 by 8 array. So 8 by 8 basis functions and 8 by 8 arrays. And then like in our first video where we constructed the basis functions from a vector x and y and a frequency k, we can do the same here. So we can go over our array. We need to define a k. So remember, k goes from 0 to n-1, where n is the total number of elements along a given direction. So in this case, just the block size. So k will be 0, 1, 2, 3, 4, 5, 6, 7. If you remember from the first video, the formula for the discrete Fourier transform was given by this. So the outer product of these two individual arrays over all the different vectors. Okay. Go ahead and run that. We won't see much, but what we do see now is that our basis functions is indeed an 8 by 8 array. Let's go ahead and say basis functions. Let's just take the first one. That should be an array filled with just ones. Likewise, basis function 1, not very clear. But this is a basis function which varies along the x direction. What we want to do now is create our output plot. So I'll copy this over. Basically, we're going to create a figure that's 16 inches by 8 inches, so 6 inches wide, 8 inches tall. We're going to use a grid spec. And this is interesting. So we're going to say that this plot has the potential to contain 8 rows and 16 columns. That's what block size and twice the block size means. But what we're going to do is we're going to make the picture of the image take up 8 by 8 of these blocks, 8 of these possible image sites, and then the remaining 8 by 8 on the right hand side each one of those will contain a basis function. We'll need a way to store our axes. We want to be able to reference these axes objects, again, because we want to be able to highlight a basis function on the actual plot to show which current basis function we're dealing with. And then we've got a lovely bit of code here. So what this does, it loops over the basis indices, x and y, which are given by the block size. So 0 to 7 inclusive and 0 to 7 inclusive, using iter tools to do this. So we can just do tools of product, and it will give us a nice array. So if I just quickly plot that for anyone who doesn't know what iter tools does, let's give a quick. We see it just returns pairs of each individual range that was given to it, but in one line instead of two. So it's the equivalent of a nested for loop, but in one line, so the indentation isn't as extreme. Then what we do is we go and say, create an axis by adding a subplot to our figure at the position of the grid size. Okay, so you remember it's 0 here, 16 here. We're basically saying start at 8, and then go 9, 10, 11, 12, 13, 14, 15. And then again start at 8, but then go 1 below it, and then do the same, etc., etc. Will all become clear once we plot it. We're going to completely remove the x ticks and y ticks for our basis functions. We're going to set the aspect ratio of 1 because these are 8 by 8 pixel images, so we want to make sure they look like squares. And then we go ahead and do an ax.imShow. So we're basically going to put the real part of this basis function yx. And remember, these basis functions is an 8 by 8 by 8 by 8 matrix, in which the first two indices are locating the basis function, and then the last two indices are locating the actual spatial distribution of that function. So we're basically plotting the spatial distribution of that particular basis function. Again, making sure we're careful with our extent. We're going to set the colour limit from -1 to 1. So we know the basis function will vary from -1 to 1, just by its definition of using these complex sinusoids, complex waves. And then we're going to store that basis function axis object inside our axes array. If that's not clear what it does, let's have a look. And one thing we need to do is we need to go back to the top because we need grid spec from the matplotlib plotting library. And now if we look at this, this is exactly what we want. So on the left, there's some space here for another plot. So there's technically 8 by 8 possible plots that could go there, but we're going to say put one plot there and have it 8 by 8 row span and column span. But on the right, we see that we have our basis functions all plotted out. So our basis functions in the x direction, our basis function in the y direction, and then our mixed basis functions here. You can also see how the maximum frequencies is attained at the value of n/2 plus 1. And then as we go further right, it's a mirror image along this line. And these represent decreasingly large negative frequencies. Good, so it looks like we have our basis functions. Okay, and now we have our base functions. So basically each block in our original image is going to be made up of several basis functions. So each block, for example, here, is going to be some combination of every single one of these 64 basis functions. And the amplitudes of every single one of these 64 basis functions is given by the value in each one of these 64 pixels. So this pixel here tells us how much of this entire function, this 8 by 8 function, needs to be added to this block. Likewise, the next pixel tells us how much of this basis function, this 8 by 8 basis function, needs to be added to this block. That goes over all possible values of the DFT in that block for all possible 8 by 8 basis functions, and then that will reconstruct that particular image within that block. So it's basically doing the discrete Fourier transform of very, very small 8 by 8 images and then tiling them together. And now what we want is we want some way to actually plot them sensibly. If I open this up again, we can see that on the right, we have these base functions that go that go up in terms of frequency. So here it goes positive x, positive y, positive x and y. Peaking out here, we want some way to be able to choose the lowest frequencies first, because in general, the frequencies within an individual block are going to favour the lower frequencies first. They tend to contain more of the information. before going to the high frequencies. So we need a way to iterate through this in terms of the actual magnitude of the frequency. One approach could be to do something like a zigzag, but then the frequencies at this side poses a problem because the frequency here, here, here are all the same. Sorry, 1, 2, 3, 4 are all the same. This frequency here should be in between these two, these two, these two, and these two. And so we need some way of ordering them. So there's a really nice way we can do this. I'll copy over a little hash box that basically says we're going to generate a list of indices that sort the DFT coefficients, and I'll explicitly write 8 by 8 DFT coefficients by frequency. So again, we're going to call it frames, and we're going to pre-allocate it. Let's see what frames is. Okay, so we can see it's basically generated a list of all possible indices. It's using that iter tools. So index 0, 0, 0, 1, 0, 2. So it's just counting along, going from left to right, row to row. Counting along, going here, 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 here. But that's not ordered. That's not a good order. So what we need to do is we need to find the frequency for all of the basis functions. We then need to go over our empty frequency array and say, this is the frequency for this particular basis function. And we know the frequency of the basis function, square root of, and then in brackets, the frequency in the x direction squared plus the frequency in the y direction squared. And we know the frequency because we know in the middle it peaked at the value n over 2. So we know it peaked at the value of n over 2. And then here it decreased by a small amount. Here it decreased by the same small amount. So it's centered around here, n equals n over 2. And we know that k goes from 0 to n not inclusive. And so here the peak frequency is going to be at 4. 4, 4 is going to be the peak frequency. And then going out from around this area, the frequency decreases. But we can calculate it because we know the frequency here is 4, 3, 2, 1, 0, 4, 3, 2, 1, 0, 1, 2, 3, 4, 3, 2, 1, or more specifically, 0, 1, 2, 3, 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, minus 3, minus 2, minus 1, and same here, 0, 1, 1, 2, 2, 3, 3, 4, 4, minus 3, 3, minus 2, 2, minus 1, 1. So they're all the frequencies that are present. So what we do is we go ahead and calculate them and store them in a list called frequencies. And that's now really easy because then we can sort the list of frequencies using argsort. So argsort will give you the indices required to sort an array from smallest to largest. And then we can apply this return from the argsort into our original frames, which lists the indices just dumbly. And it will tell us how we can sort our frames, our indices, such that the list goes from smallest to largest. And simply by flipping that argument sort list, we can get it so it goes from smallest to largest. And now let's have a look. Frames is now something a lot more sensible. It's now ordered by frequency with the lowest frequency first, lowest frequency index first, and the highest frequency index last. 4, 4. Good. So we know that's working. What we're going to do now is we're going to do the plot. So I'm going to spice things up in this plot. We're going to enable blitting. That just means only update the plot where things have changed, because I found that you get a nice effect when using blitting this way, which I haven't managed to figure out, but I think it would be quite nice to keep it. And then we're going to do something like this. So in fact, we can copy over a lot of our code from our previous example, particularly this. Remember, we have an update function that says what must happen between every frame of the plot. But this time we're going to enable blitting. We're going to say do 2 FPS. Don't need to list that. We're going to send it to the image 3. So every time the plot wants to update, it comes into this update function. We're going to give it a tuple, which will be the frame number and the indices required to sort it. And we're also going to send it the image 3 array. So this will be the image that we're building based on these basis functions. Okay. We're then going to do some tuple unpacking to get our value of n, which remember is the current frame number, so this will be useful for saving. And then we're also going to get our index y and x. And remember, y is rows and x is columns. So when we get our index, that gives us the next basis function. We need to remember that this is y and x indexed in that order. Very, very important to remember. Now, what we need to do, let's do something a bit more graphical for now. Let's see if this is working. So we can do something here. We can say each of these little subplots, each of these little boxes, these little basis functions, you see it has a black line around it, and that's called, in matplotlib terms, a spine. So it would be nice if when we come into this function, we're given a tuple which contains the index of the basis functions ordered from smallest to highest frequency. It'd be nice if we could actually just show that working. So if I go ahead and look at this, let's extract the spines of that particular axes, because remember we saved the axes earlier on when we created them, and we're going to set the edge color to red. Give it a nice thick line width, and also bring the Z order up. So set it to a Z order of 10 just to ensure that it draws above everything else. If I go ahead and plot that, we should see nothing apparently. And that's because we've done something very silly. We've enabled blitting, so we're telling the plots that only change the things, only update the things that have changed, but then we've not told it what's changed. So we need to tell it that these axes object has changed because we've changed its spine. And there we go. It's successfully iterating through each one of these basis functions. So it's showing you which one of these has currently been accessed. Small graphical problem there in which it disappeared. Same again. But you get the idea. It looks like it's also in the correct order. It's choosing the lowest frequencies first, then moving on to the highest frequencies. That looks like it's working. Next task is to actually go ahead and update our image on the left. So to do that, we do this function. So we're going to do a double for loop in this case, which I suppose should have really been done with a itertools product. Quickly change that. We're going to loop over the entire image in blocks. So going from 0 to ny in rows and 0 to nx in columns, but in steps of 8. For each one of those blocks, we're going to add on the basis function, which is now indexed by this basis index y and x, which is the current basis function that's been requested to be plotted, times the value of the block-based FFT at that particular block at that particular index. We then need to go ahead and set the image to the new real part of image 3, and that should be enough. When we go ahead and plot that, it doesn't work. And that's because we never actually created the image on the left. What we need to do, copy some code over. So the axis, so we'll call it ax, so this will be our main axis, is going to be on the grid spec, so it's going to take up all the rows on the left-hand side of the image, but then it's only going to take up the first 8 columns, because remember the last 8 columns are used for our basis functions on the right. And then it's going to show it the image 3, which is just blank, so we would initialize that to 0. Set the color limit from 0 to 1, because we know our original image should be from 0 to 1, and so when reconstructing it, 0 to 1 should be the appropriate range. Then we're going to remove the tick labels. Go ahead and plot that. This should work. And there we go. We can see we're successfully reconstructing the original image from individual blocks. So every time this red box highlights one of these basis functions, it adds on this basis function to every single block with the amplitude determined by the amplitude within the corresponding block at the corresponding index. And these are complex amplitudes, but then the resulting image, we take the real part, and what we end up with is our ability to reconstruct the original image, but now in a block-based DFT. And if we look, before when we had hardly any information describing our original plot, we had artifacts all over the entire image. Now we've localized the artifacts to around the text itself. So you'll see this quite a lot. If you have high compression, say JPEG image, which uses the discrete cosine transformation, which is very similar, you see that the JPEG compression attenuates a lot of this high frequency information. So this is typically the information here, which we have not yet plotted. We see these blocking artifacts. So it comes from the same phenomenon. But the rest of the image is now left pristine, because here where we had this 8x8 block, so we only needed one lot of basis function, which was this first one with an amplitude of 0 to describe it. Likewise, if the background was white, we would just need this block here with an amplitude of 1, this basis function, to completely describe that 8x8 block of the image. So we can see how breaking the image down into 8x8 blocks and doing discrete Fourier transform of each block has massively helped us. And now this has helped us with our original image. So remember our original image when we just did the DFT and started removing components. So here we're adding components, but it's the same process. You can see we had horrible artifacts over the entire image. But now we've localized those. And if you imagine now if this image was zoomed out, those artifacts become even less noticeable. So we've done a very good job here. And if we go back up to the top and we do our picture of ducks instead, look at this. Look how quickly the image becomes good quality when doing this 8x8 block-based DFT. So before, the DFT could sustain decimation of data up to around 95%, so we only need about 5% of the data before it actually looks good. And likewise, in this block-based FFT, we really only need 2 or 3 elements in order to be able to see the original image. If you look here, we can see that the image is almost back to its original quality. The thing to watch out for, I'll play this again, just watch out for around this middle central duck's neck. So look around the neck. You can see here, we can see a line. And that's a compression artifact, that's like a block artifact, but that will go about now. So now it's gone, and now this image looks almost unrecognizable from the original image. And so all these extra blocks that we're adding are basically useless, and which is kind of what we expect, because in the original DFT, we did see how removing most of the data barely affected the image. So this really shows you how powerful this block-based approach is. We can maintain the same immense, I don't want to necessarily say compressibility, but the immense ability to remove loads of data, but also be able to do the same for an image. So remember, the image now is actually legible for the same sort of level of decimation. And what we see here as well is that most of the data required for this background comes from 0 coefficients of these basis functions. So it stands to reason a compression algorithm could quite easily set all of these blocks here to just 0, and then use a small amount of information from the DFT to regain this original text. Even if we required all the components to generate the text, that's still a massive saving from before when we had the full DFT, where we had artifacts across the entire image until we restored every single one of these original basis functions. So that really shows you how good this block-based approach is. And so removing DFT components on block-based digital photographs can be just as good as removing components on the actual full DFT. And for simple images, this block-based approach looks like it's going to result in our ability to actually remove far more of the data from the DFT than we could with a non-block-based approach, because we can use more data, or we can use the full data for where the text is, but then considerably less data where the text isn't, without any artifacts across the entire image. And so in the next video, what we'll do is we'll actually show the difference between removing information based from each block compared to removing information from the full DFT for the same image. And we'll see how the block-based approach actually leads to a really good reduction in image size for both text-based images and digital photographs. So stay tuned for that video, you don't want to miss that. Thanks for watching.